Okay. Are we are we live? Yeah, I guess we are. Um just hold up a second before I just kind of fix everything. And yeah, this looks good. Looks good. So this was what we were doing last time. We were having a look at some little bit of category theory because I was really sleepy and did not want to talk some talk about things which require mental faculties. So I just decided to rant about what I already knew. Now, what are we doing today? We are doing some tilings. Okay, so um, I'll be reading some tiling stuff, and a particular conversation has already happened somewhere. I want to understand what has been said there, and kind of all that. A lot has been said, I guess. So yeah, let's get started. Just to make things clear, first of all. Yo, let's go, bruh. Okay, so since we are doing tilings, we should cover the random lozenges. Um, Wait a second, just hold on a sec. Okay, so the thing is, I was actually planning to uh, revisit things which have already happened. So, like the papers given and the slides, and especially the enlightening conversation that has happened in the group, and all the unlatexed mathematics. So that needs to be deciphered, I guess. Um, yeah, yeah, we can actually. Okay, okay, not a bad idea. Not at all. Let me see. Okay. To fix this, I wonder who did that. Yeah, that's right. But I've got a lot of stuff to do anyway. So yeah, better to start. Just not that. Okay. Let's try this. The obsidian one. Yeah, sure. Yo, let's go.
Yeah, am I audible?
Yeah, you are.
Yeah,
Just
so as I was
hold on a
saying,
sec.
the presentations have been moved till Saturday, so
Yeah, I know.
time to
Heard the stuff.
we'll probably do the text by Goran today.
Yeah. Okay.
Random loss. Silence.
Okay.
Yeah, so let's just read through it and discuss it in regular time intervals.
Yeah, sure. Just hold on a second. Just hold on a second. Yeah. Okay. Looks good. I just need to figure out how to fix the scaling of the frame. Okay. Okay, that's horrible. Okay. আচ্ছা, তোর নামিয়েতে দেখালে অসুবিধা নেই তো?
দেখাস না।
আচ্ছা, ওকে। তোর অন্য কোনো অ্যাকাউন্ট আছে, মানে যেটা দিয়ে জয়েন করতে পারবি?
আমার তারা অন্যটাতে ঢুকছে না।
হ্যাঁ, yeah. So yeah, in short, the thing is that um, the other person who joined, for others in the stream, if anyone is there, he's an absolute giant, my classmate, and absolutely great guy. And he doesn't really want me to show his name. So yeah, okay. Anyway, I will edit this part out anyway. All this until we actually start doing tilings. So yeah, just making sure stuff is okay. Okay, well,
Action principle roughly states that
sorry.
Imagine.
Very, very weird stuff. Yeah. Okay. Yeah, I guess we are starting. So, the regarding tilings, just wait a second, I might increase the brightness a bit. Yeah, okay. So, um, okay, so a lot of stuff happened in tilings. We did a lot of things. First of all, um, what tilings are. So that includes what is a tiling, what is a tiling, what is a tile, tile. There you get things like monotiles, so basically your tile templates and all that, which you copy around and do stuff like this. You see various kinds of tilings, as in regular, some regular tilings, some semi-regular tilings, and some irregular tilings. On top of that, we sometimes have other things like water faults. So these are usually uh, tilings of entire spaces. Think of, say, R2 or just entire Arden spaces, or sometimes other projective spaces or complex spaces. But we are initially keeping the things simple and considering spaces and convex subsets of Rn and sometimes affine spaces. And then we see what faults are. So these are just tilings of rectangles. So this is m cross n rectangles in R2. So, absolutely standard stuff. You have rectangles, you have all these bars and cells, and we tile all of them. And so all of these rectangles, all of these tiles are of the same size. And sometimes we look at domino tilings and other kinds of tilings, stuff like that. So faults and other matters of interest include fault-free tilings. And last time I was looking at a paper that discussed basically entirely the number of fault-free tilings, vertically fault-free tilings, and symmetrically you can just talk about horizontally fault-free tilings of 3 cross n rectangles. So that basically looks like this. It is a very long, or like how long that depends on your n, and there are 3 rows like that, and you do domino tilings. So not just domino, when doing domino tilings, if you have to be fault free, then there is practically only one kind of tiling possible that looks like this. So to be fault free here, you cannot go with this tiling, that will give a vertical fault like this. So you have to go like this. So you tile like that, then you have to go this as well, you're forced to do that, and then you have to go this, then this. So it basically progresses like that. And link expired, let me know when you start random tilings. So I'll read ahead a bit. Okay, random tilings, I'll see what I can cover today. The stream will not be very long because it's already like 6 and I'll have to go by 7:30, but we'll probably resume after, I don't know, 8 or something. Yeah, so why did the links expire? Link as in the Google Meet. How did that expire? Just a second. I guess I did not get any notification about someone joining. Yeah, okay, sure. Okay. Okay, so anyway, this was the stuff I have already looked at, and I guess it is not a feline, it's a corvus. Yeah, actually I have no idea about what kind of background noise is in there because I have not played the stream anywhere. So I guess I'll just give it an ear. Feline, it's a corvus. Okay, yeah. So that's just a crow. I practically can't do anything about that. That's a damn crow. Anyway, uh, what's next? What are we doing next? We are looking at uh, the stuff that has been talked about after that. Because we have had only one session. And after that, there was some stuff. Asymptotics of domino tilings isn't tends to infinity. Okay. The number of runs are valid. Okay. There's usual identity states with m binary strings. We want to know the number of states which we can reach from some state B in one move. Okay, yeah. So let's have a look at some the states information of tilings. So currently we are considering domino tilings. That is, all of the monotiles look like this. So the cells look like this. There are basically just two squares adjacent. And what is a state actually? So suppose we have the board which we are tiling is rectangular and looks like this. All of this are tilings of just m cross n rectangles. So that is what we are tiling. And m is measured this way, n is measured that way. So what we do actually, we look at all of these vertical lines, and for each vertical lines we start at 0 and go up to n, and for each integer from 0 to n we assign basically a string, a list, a vector, whichever you call it, s, say I. And s, what si does is that si stands here at say the ith position. If a domino crosses it, so if there is a domino which crosses this ith line, so this says if there is a domino. Okay, so we are actually this way m, and we look at each cell. So the cells are numbered 1, 2 up to m, and for each cell j, if there is a domino at let's say height, let's call it height, at height j, such that it is placed at, or such that the domino covers these two cells. So at height j, suppose the domino covers these two cells. So which cells are these? 1, 2. So okay, the cells are I and I plus 1. So we start counting. The cell numbering starts here at 1, and the exact number to the right, or the right edge of the cell, has the same number as the cell's count. So if the domino covers the cell I comma j and I plus 1 comma j, then we say that si, the jth at the jth position, or just sij, that is equal to 1 and otherwise 0. So what this really does is that it has been claimed that this gives a complete description of the entire tiling of the board. So how is that? So notice that I'll just try and draw a grid once and for all. I guess that would solve it. Let's do this. Yeah. Let's draw another one here. Like that. Okay. That's pretty horrible. Okay, something happened. doing? No. This is doomed. No way. Oh, what is that? Okay, now I really messed up. Now I really messed up. Okay. Fine. What am I even doing? Oh, great. Yeah. Let's just cut that. Okay. Not very meaningful activities going on with all the limited time. Just give a last attempt at trying to copy this to somewhere else so that I can actually okay, let's just get this out. Yeah, nice. Wow, there we go. Okay, looks fine. looks fine. We can work with that. So what was I even talking about? Yeah, the states. So when you start at the 0th position, there is no domino crossing these lines because the board literally starts from here. So what you do is you get that S0 is just all zeros. So at all positions of the first vector, you get just zeros. Then at the next position, let's say at 1, there might be some dominoes which go like this, and there might be some which stay up aligned like this. So yeah, if there is a domino at, let's say, the jth position such that it crosses this line, we get that S1j, that is equal to 1. And if there is no domino which crosses this line, then we have to know that that there is a vertical domino at that position. So from, let's say, all zeros, from this kind of a configuration, let's say there are 5, so we are dealing with some kind of a 5 cross n board where you start with all zeros. Then you get the situation 1 1 0 0 1. This is possible. This is S0, this is S1. This is possible because it is possible that after the first domino is like this, and then you get something like this, and then again something like this. So this kind of a configuration is actually possible. What is not possible is to have something like this and a 1 here. So the 0 cannot come alone. If there is a 0, it has to basically be paired with another 0. So this kind of a transition, this is not possible. Okay, and currently in the thing we are I'm looking at, we are talking about possible which states can follow which states and which state configurations are possible and which are not. So let's read what has been given. There is an issue. I consider the number of runs are valid. 3 and 5 is valid clearly. Only j comma k is valid. Where? Okay. What are runs? Does it start before that? It does not. Suddenly we're talking about some runs which I have no idea what these runs are. Okay. Also, along with this, there is a thing called the tiling matrix. What it does is you consider all of the states, like all the S vectors, and put that into a matrix and call it a day. That is what a tiling matrix is. So let's say let's select a 5 cross 5 board out of it. Let's say like this. So this is the board that we are considering here. let's say the tiles are positioned like this. Okay, cannot do that. Let's say something like that. Okay, let's say we have a tiling like this, and what are we looking at? We have to create the transition state matrix. Okay, the same thing, I guess. Does not matter much. Just you put all of the S vectors and call it a day, I guess. So you can put all of the matrices in this form. So this is not really matrix, as in this does not really represent a linear map of spaces in any way. So this is just a combined list of numbers, something like that. There are eight vectors. Okay, so the first one has to be 0 all the way, the last one as well, because that is really the border of the tilings. Then we see that that two tiles cross the first line here and here, then two zeros and then another one, and the next one has 0 0 because these two are not crossed. Then you get 1 1 and then another 0, I guess. What else? You get all 4 zeros and a 1. We get a 1 and then 4 zeros. Then we get 0 1 1 0 1. At the 6th position I get 1 0 0 0 1, and in the end we get all zeros followed by 1. So I guess that is the thing. These are all the S vectors. But that does not make much sense anyway. Okay, I guess. Okay. So in an S vector, we are looking at the number of runs of zeros and ones, and clearly it has to be the case that either uh, the number of runs of 0 is equal to uh, the number of runs of 1 plus either 1 or 0 or minus 1. So it can differ by at most 1, because a run of 0 then a run of 1, they have to be alternating in some way. So there can be either, it could end with any of them, and there could be at most one excess. So you cannot have 2 runs of 1 consecutively, because that would be just one run. Okay, so we get that. What is it? As the usual identity states with m binary strings, we want to know the number of states which we can reach from some state B in one move. If there is a run of ones in B, this part is fixed, and the next state will have zeros in the place of these ones. Okay, so what is being said is that if we have some ones in a state, then the next follow-up has to be 0 in those positions. Why is that the case? That is primarily because when there is a domino, suppose these are your state lines which you are looking at, there is a domino which crosses this line here. There is no way there is another domino which crosses this, because that would cause an overlap of dominoes. So this is not possible. What is possible is that there is some domino like this, and then you have a domino which looks like this. Or on the other hand, it could happen that there is a domino like this, so there is a 1 here, then there is a 0 here, and then you could follow up with a 1 here, just like what happened here, a 1 and then a 0 and then a 1. So there is a domino which is like this, and then there is a domino which is like this. So that is possible. Okay, so I guess I made some nice mistakes here. Okay, yeah, there's a mistake here. This would be 1 and this is 0. So 1 is always followed by a 0. But if there is a run of zeros, then we can correspond the number of new states of this run alone can give rise to what? Then we can correspond the number of new states this run alone gives rise to with the number of tilings of length of run times 1 strip, which is the Fibonacci number with index length of this run. Okay, not sure exactly what is being said there. Let's read again. This, if there is a run of ones in B, then this part is fixed and the next state will have zeros in these places of ones. Okay, but if there is a run of zeros, then we can correspond the number of new states this run alone can give rise to with the number of tilings of length of run cross 1 strip. Why is that the case? So suppose consider any run of zeros. Let's clear this situation up a bit. Yeah, okay, now let's consider a run of zeros such as this one. Then we can correspond the number of new states this run alone can give rise to with the number of tilings of length of run cross 1 strip. Okay, So what is this? This says that if there is a run like this here, then in the next state exactly this part has a configuration like this. And what can be this configuration? This configuration says will have the same kind of configuration corresponding to the number of new states this run alone can give rise to, with the number of tilings of the length of run cross one strip with 2 cross 1 and 1 cross 1 tiles. So why is that the case? This is the case because you can place after there is a run of zeros. So let's say in this case, what is S4? 1, 2, 3, 4. So after this fault line, not really a fault line, after this basically after these 0 states, the next possible situation here looks like this. There is a domino like this, the white one. There is a domino in the bottom which looks like this, the orange one, and there is a domino, the green one, which looks like this. Now since we are tiling entirely with dominoes, we can just extract just this part, this column. We can just extract this column and look at the tiling situation here. Here when there is a 1 cross 1 tile, so if there is just a square tile, then we know that this tile is a domino which is placed like this, because there is nothing previous to it. This part is 0, these are all zeros, so there is no domino which is like this. So it is necessarily the case that some domino lies like this. So a 1 cross 1 tile exactly corresponds with this. And if there is a domino placed here, well, then there is a domino placed here. So we get a 2 cross 1 tile here, and again here is a square, so there must be a domino like this. So basically, if there is a run of zeros such as this, if there is a run of zeros, let's say at SI the run is from J1 to J2. Okay, that's a J1 to JK. Let's say the run of zeros looks like this. So then if we look at SI plus 1, the number of possible configurations of these positions, so we just look at starting from J1 up to JK. We don't need a different indexing here though. Yeah, so okay, leave that. Up to J plus K. Yeah, that makes sense. Up to J plus K. So the number of tilings, number of possible tilings of this is if there is a number of zeros, then number of possible configurations is given by the number of tilings of this of basically this part J up to J plus K by dominoes. So this is just a column. This is just a column of length K plus 1 cross 1 by dominoes and squares. Now there is one subtle catch here which needs to be addressed. So this is not really a problem, but this could be problematic in some situations. We do not address this, which is, suppose there is a run of zeros as in here. Okay, not really. Let me just okay, yeah, okay, let's look at this run of zeros. Not this either. What the hell? It looks like this particular example does not turn out to be that helpful. Okay, so suppose the situation is like this. Here we have a clean fault up to, say, starting from j up to j plus k, and here there are some tiles like this. Let's say like this, and at the last position there is a tile which goes like this. Now if this was the case, then if you look at just this column here, then this column recognizes this part as being tiled by a square, then by a domino, then by two squares, and then by another square. But the problem is that this domino here, this square contributed to this tiling could be because of a domino like this, or it could be because of a domino like this. Now in this situation, because it is a complete run of zeros, we know that there is a 1 here, so there is a domino already placed like this. So it cannot be that this this square is being contributed by a vertical domino. So we really confirm that this has to be a horizontal domino. Okay, so that is not a problem. That was just one thing that I was slightly concerned by. So yeah, what is next? Which is f, which is okay. So let's count how many tilings are there. So this is just a counting problem, which is we have a strip of length k cross 1, and we either tile it by dominoes or tile it by squares. So either tile it by dominoes or by squares, and the number of possible so the number of possible tilings of this column is just given by the Fibonacci number sub k, which the reason being that if the first tile, when you look at the most bottommost position, it is either tiled by square or it is tiled by domino. If it is tiled by a square, then you have to have a tiling of k minus 1. So there is a k minus 1 here, and if it is tiled by a domino, then you have to have a tiling of length k minus 2. So you get here k minus 2. So this is this really indeed is the Fibonacci sequence, and the base case also satisfies, because for a length of 1 cross 1 you can there is only one way to tile it, and for a board of size 2 cross 1 there are two ways to tile it, either by one domino and by two squares. So this is indeed the Fibonacci sequence, and the number of ways of tiling k cross 1 column by dominoes or squares is indeed Fibonacci f sub k. With this, let f of b equal to f sub r1 up to f sub rk, where ri are the lengths of runs of 0. Ri are the lengths of the runs of 0. Okay. So what is being stated here is that given a state vector, Si, if there are some ones, then it is uniquely determined that in those positions in the next state vector there will be zeros. And if there is a run of zeros, then there can be let's say a run of length k, then there can be f sub k distinct then there basically can be f sub k number of distinct possible next states. So given any state Si, how many possible states can we have next? That is to say, first you count the number of ones, the number of ones in total. Let's say that is given by, okay, so first of all let's fix a number. The height, the height of the board is m, and let's say the number of ones in this state Si is k. So the number of zeros is m minus k. Now how many distinct runs of m minus k is possible? That is to say the number of partitions of m minus k. So we are looking at natural numbers, let's say x1 up to any number of runs. Let's say there are r runs, and all of these have to sum to m minus k, and these are distinct natural numbers. There are some bounds on what this number r can be. Since we are choosing r to be the number of runs of 0, it is clearly that since this is the number of 0 runs, this is less than equal to the number of 1 runs plus 1, and also it is greater than equal to number of 1 runs minus 1. And how many 1 runs are even possible? That is, if all of the ones are just separated, so separated by zeros. So there is a 1, then there are some zeros, and then there is a 1, then there are some zeros, then there are 1. So no two ones are consecutive. That is when the most number of 1 runs are possible. That is to say, it is at most k plus 1. And since the least number of 1 runs that is possible is 1, because there has to be at least 1 run of 1s, or okay, is that even necessary? There can be 0. Okay, yeah, anyway, the thing is that r cannot be 0, or can it be? Yeah, r can be 0. Yeah, so the lower bound is always just 1, always just 0, no matter what. So r is between k plus 1 and 0. Looks like something happened. Just wait a second. Okay, never mind. Someone was calling. Just hold on a second. Okay, don't go down the partition path, it leads to nowhere. Okay, sure. I'm not going down anywhere, I'm just reading what you wrote there. Okay, so these are the number of runs, whatever, number of partitions or whatever that might be. And then in the end you have to take this these counts, f of x1, f of x2 up to f of xr. And since this partition formula does not really give the exact values of these x's, I think this product is not something one can evaluate directly from this. So that is one way which does not work. Yeah, thanks for the reminder, by the way. Are we still actually live? Like, has it closed or something? Is it still going on? I guess it is going on. Yeah, okay, great. What is next? Then the number of achievable states from this S1 runs and T0 runs, which might be 0, is x to the m2. Okay, that is not something very readable right there. What is x to the m? Okay, that is a generating function. A2 a 2 is there if and only if a is equal to t. J of x minus 1 to the s, f of x minus 1 to the t, where I of x, okay, when j of x equals x plus x square. Okay, so that is a huge generating function. Start with a run of 1. Okay, x to the b, sum of all graph, then it goes to minor strings. Okay, I don't think this is going to go well. So what we are after all doing is we are counting the all of this. What all of this is doing, this is counting the number of possible states followed by a given state. Counting, can't spell counting, number of possible states s I plus 1 given a state si. Okay, that counts that. This is the generating function of the number of edges in the state diagram for a tiling and crossing matrix with dominoes, I believe in similar methods. Mth Bell number. Okay, I guess I'll just ask him to explain it the next day. Main use of minimal and characteristic polynomial is basically to check if we have redundant states in the state space or not. If minimal polynomial is much smaller than the characteristic polynomial, then there exist redundant states. Okay. Eigenvectors correspond to dominant boundary types in larger tiles. The eigenvalue spectrum and characteristic polynomial can be used to exact GF and find the current relation. Okay. Okay. Yeah. Okay, we are back. Let me just fetch the actual presentation paper which was given that day. So I'll just close this for a second. Yeah. Okay, so this is the stuff. Encoding tilings. Yeah, this is where we were. Okay, to count the tilings of an m cross n rectangle by dominoes, we build the tiling column by column and a vertical cut between the columns and k plus 1. Some cells may be occupied by horizontal dominoes in these positions. Okay. Legal placements of dominoes in the next column determine which states can follow which. As be this corresponding transfer matrix. A has entries. Okay, so from here, okay, so the other thing we looked at, it was basically complete nonsense. Where did the node go? Just a second. Anyway, never mind. Yeah, okay. So instead of forming a matrix like this, we do not really do that because this matrix does not really represent any kind of a linear map or anything. What we instead do is we collect all the possible states. So we collect all the possible states and look at which can follow which and form a digraph. And notice that this digraph does really have some sources and sinks, that being because any state can, okay, not any state can follow, uh, not any state can end. This diagram has a source, namely the first one, because any state can start after, uh, basically we can start tiling with any state after the S naught. There can be any possible configuration of the tilings, or can there be? Well, any state is possible if and only if this height m is even when we are tiling by dominoes. That is because then the 0 0, then basically S naught will be able to follow S naught. Okay, so that is not very interesting. What is interesting if we form basically the adjacency matrix of this uh, of these states, and this adjacency matrix gives us much more spectral details about exactly which states can follow which, and that gives a much more better refinement of what we are looking for. Okay, that is a good way. Similar methods can be used, but the hard part is constructing a non-redundant transfer graph. If we use k times one tile, then bi in state s text values, yeah, up to. Okay, so what is going on here? is that instead of just dominoes, if we allow tiles of size, let's say k times 1, if we allow these tiles of length k and width 1, then for any particular state Si, we will have to note exactly not just the fact that if a tile actually intersects that line, but also how far to the right of that intersection the tile is. So it might be that no tile intersects this line, something is like this, or it might be there are just a few squares, it might be there's just one square after this intersection, there might be two, all the way up to that there might be just one square to the left of this intersection, and there are k minus 1 positions here. So in that case, these SI vectors are not really just 0, 1 vectors. They could be, so Sij will be from 0 up to k minus 1. That is that. And as usual, since the number of possible values of this gets higher and higher, we expect that the number of possibilities and the complexity and the just general complexity of the graph, of the directed graph or the transition states, can basically go up by some exponential factors of the size of the tile. So we expect that the complexity goes up exponentially with the length of the tiles. And then comes also the fact that there can be multiple tiles used, so not just some k cross 1, but let's say there are many tiles used of the form ki cross I, or even better, you get more general tiles. So with I going within some range of numbers, you get tiles of all sizes ki cross li. So there are tiles of many shapes and forms like this. That raises the complexity even higher. Similarly, if we move on to other tileable spaces and other shapes and even rectangles, we consider A times B tiles or L-shaped tiles. Yeah, the shape of the tiles also matter. It could be from rectangles up to all kinds of bizarre shapes. That could be monotiles. So yeah, that is also there. So the Tetris friends, yeah, which remains an open problem for the last 40 years. Okay, fault-free tilings, which remains an open problem for the last 40 years at least, even within domino tilings of rectangles. Getting a general function for domino tilings of m cross n rectangles was easier solely because every fault line you need at least one domino to counter it, be horizontal or vertical fault, which for larger tiles correspondence is not so one-to-one. Okay, so what is exactly going on? The thing being said is that if there is a fault in the tiling, so there is a one line which completely separates the tiling into two parts. If there is not such fault, then there must be a domino which exactly lies like this. So it blocks this line, so this line cannot really cut the vectors. So it says that for any vertical line like this, there is one domino like this. So other than the first state and the last state, all of the other states have to have at least somewhere a 1. That is what it really says, and that is required for a fault-free tiling, or at least vertically fault-free tiling. To have horizontally fault-free tiling, it has to be the case if there is no horizontal faults, then for every height like this there has to be some tile which is vertical. And since we are keeping track of only the horizontal tiles or the horizontal placements of the tiles from exactly the forms of these state vectors Si, it is not very easy to comment if there is some vertical tile or not. You have to check state by state and figure out where exactly the vertical tiles are. Okay, that is another nice comment right there. It says that domino tilings correspond to matchings. Subdivide the entire rectangle. So you take the entire board into all the unit squares, and whenever you place a domino, basically, uh, let's say you create a grid out of this rectangle. So each of these cells are now shrunk to a grid, and in this grid, any 2 points are connected by a line if there is a domino which uh, occupies both of these squares. So this is kind of that. Okay, if we fill out the entire board like this, then we will see something like this, and that is essentially a matching of the different parts of the rectangle. So this segregates out all of the squares into one of two groups, so we get some groups here, some groups here, and exactly there has to be one-to-one matchings. So we take this domino problem and put it into a, we can basically take this to a bipartite graph situation. But if the tiles are not dominoes, if they are much more complicated than that, then let's say there are 3 tiles, so tiles of length 3, and then how do you really model this in terms of some matchings of vertices of some graph? So you still create a grid out of this, and let's say you get matchings like this. But then there is no clear way to say that these three vertices uh, are exactly concurrent, or what is that called even? These 3 vertices are collinear or are joined by like one big edge. And graph theory does not really allow that kind of a correspondence. So that is much more of a problem. So this is not exactly, this does not correspond exactly with, let's say, a tripartite graph, because then you get situations like this, which is not possible for tiling, but this is a valid configuration in the tripartite matching. So the matchings only work because we are dealing with dominoes. Okay, there's that. Okay, there's quite an inspired amount of mathematics going on here, which does not look very readable on the surface though. So I guess I'll just skip that. Yeah, it is that. Random Lothian stylings. We shall meet again. Okay. Is there a notion of perfect groupings instead of perfect matching two connected edges if we talk about clique subgraphs? I'm not very well informed about that. There is a thing. Send some clarification, by the way. Just a second. Oh, okay. Bro, you sent a 5-minute long message. Okay. Okay. I'll listen to. Is there a notion of perfect groupings instead of perfect? I'm not very well informed about that. So I'm not sure if that is even possible, or the work has been done on that. Yeah, you can always look up. What are we doing next then? Let me just. What is GNS contraction? Let me look up. Contraction or construction? Okay, we don't do that here. No, I'm not looking at that. That's not happening. What are we actually supposed to be doing? We are doing tilings, right? Let's have a look at some books. Okay. Yeah, this is not visible, right? Yeah, this is not visible. Okay. Someone's fun at parties. Bro, what? Okay. First two chapters of the book, Random Lozenge Tilings. Where's Random Lozenge Tilings? guess this one. Okay, lectures on random lozenge stylings. Okay, let's go. We have been asked to read random lozenge stylings. We will read random lozenge stylings. Let's go. Introduction and tileability. Okay. The preface starts through a chapter. Okay, that's exciting. Lindström Gessel V0 lemma. This does not seem interesting. The goal of the lectures is to understand the mathematics of tilings. The general setup is to take the lattice domain and tile it with elementary blocks. For the most part, we study special case of tilings of polygonal domain of a polygonal domain with the triangular grid of mesh size 1, whatever that means, by three kinds of rhombi called lozenges. The left panel of figure 1.1, where is figure 1.1? Okay, with rhombic holes. Sure. Okay, that's the AOPS logo right there. Nice. Lozenges can be also viewed as orthogonal projections onto the x plus y plus z plane of the three sides of a unit cube. Yep. Figure 1.3 shows the lozenge tilings of a larger domain with three types of lozenges in the three different colors. Jeez, what is that? That's enormous. Okay. That's huge. The simulation reveals the interesting features. One clearly sees the next boundaries of the domain formation of the other regions, where only one type of lozenge is observed. These regions are typically referred to as frozen regions, and their boundaries are Arctic curves. The discovery and study has been one of the most important driving forces for investigation of the properties of random tilings. Okay, so we are talking about, I guess, this region. These regions were along these positions there is exactly one kind of formation possible, so you do not get too much of a variety on what you can do and what you cannot do. And similarly on the other corners, this is completely dominated by one kind of tile. That is because the corner is like this, so the lozenge placed at the corner has to look like this. Okay, so and the only way to tile nearby these corners so that it matches with this edge is to repeat just these lozenges lots and lots of times. Okay, that makes sense. That makes a lot of sense. And similarly for the other corners too. Get a green again on the top, on the bottom, because the corners look the same basically. From the top it looks like this, from the bottom it looks like this. So again, you tile it like this. Okay, that's good. A perfect sample of a uniform random tiling of a large hexagon with a hole. And as you can see near the hole, the situation is something like this. And so here we get tiles which we get lozenges which line up with this angle. We get lozenges with line up with that angle, and on top of that there is nothing. But if there had to be something, it had to be the what color is that? The green lozenges. Okay, that makes sense. Motivation. Figure 1.3 is beautiful, and as mathematics suffices for probing more deeply into it and trying to explain various features that we observe in the simulation. There are also some motivations from theoretical physics and statistical mechanics. Lozenge tilings serve as a model or a TOR model that helps in understanding the three-dimensional Ising model, a standard model for magnetism. Configurations in the configuration in the three-dimensional Ising model are assignments of plus and minus spins to a lattice, points of a domain in Z3. So basically, where the molecules are placed, you get either positive polarization or negative polarization. And that is basically the Ising model for magnetism currently. A parameter, usually called the temperature, controls how much the adjacent spins are inclined to be oriented in the same direction. The zero temperature limit lends to spins piling into as large as possible groups of the same orientation. Okay, that's some digression. Another deformation of Lozenge tilings is a 6-vertex square ice model, whose states so basically it is ice. It is the crystal structure of the ice. Mathematical questions. We now turn to describing basic questions that drive mathematical study of the tilings. Existence of tilings. Given the random domain R drawn on the triangular grid and thus consisting of finitely many triangles, does there exist a tiling of it? Okay. For example, a unit-sided hexagon is trivially tileable in two different ways, and the bottom right panel of figure 1.1 shows one of these tilings. The unit-sided hexagon is tileable in two different ways, it says. Okay, yeah. So this is one possible way to do it, and the other possible way, I guess, would be something like this, where this lozenge is basically placed at the bottom. So it is just inverting the cube in a way. So there is that. This is here and this is here. So yeah, you just rotate this cube upside down and you get something like that. Each lozenge covers exactly one black and one white triangle. Another way to prove non-tileability is by coloring the unit triangles inside R2. Okay, this is the same type of thing, I guess, when you look at a chessboard and ask if it is possible to tile the chessboard in some particular way. So why the chessboard is really helpful in these cases is because of these alternating colorings. So basically, when given a domino, let's say, when you are given a domino and asked if you can tile the chessboard with those dominoes, it is clear that basically when you're tiling a chessboard with dominoes, you separate the black squares on one side and separate the white squares on one side and create a pairing between the two. So if there is any discrepancy between the number of white squares and the number of dark squares, you get that the tiling is not possible. Something like that, I guess. Each lozenge covers one black and one white triangle, but there's an unequal number of black and white triangles in R. The equilateral triangle of side length 3 has 6 triangles of one color and 3 triangles of another color. Okay, we are tiling these by lozenges. So yeah, tiling by lozenges is basically the analog of the chessboard being tiled by dominoes. So it's the equilateral triangle of side length 3, which I hope looks like this. Side length 3 means there are triangles like this. Okay. That was really bad. What do you mean side link 3? So is it like, so is it that? The triangles here. Okay, this is like that. Okay, understandable. And if you color the triangles this way, it looks like this. Yeah, so any coloring of that has to be of this form, where there are 3 triangles of the same color and 6 triangles of the other color. Is it possible to tile it by lozenges, by the way? It is not, of course, because if you put any lozenge anywhere, that lozenge exactly covers, the lozenges create a pairing between the completely, basically, triangles of one color and the triangle of other color. So if there's some discrepancy between the number of those triangles, then you will not be able to pair up them uh, using lozenges. Okay, so that looks good. Another example shown in 1.4. So this, how many tiling does a given domain have? That is another question. Quality of the answer depends on one's taste and perhaps what one means by closed form or explicit answer. Okay, so there's a cat outside my room right now. I'll just be back in a second. Okay, so here we get this theorem due to McMahon, and it gives definitely not a closed form of what we want, but okay. Then we get some probabilistic stuff, law of large numbers, the height function, uniform distribution. Okay. Which regions are liquid? That is, contain all 3 types of lozenges. What is the shape of the Arctic curve, the boundary between frozen liquid regions? For example, with AL cross BL cross CL hexagon setup, one can visually see the boundary appears to be inscribed to an inscribed ellipse. Does it? Okay, yeah, the boundary looks like a circle here. That makes sense. Okay. I guess we'll end this now, and I'll come back after some time. So